Automated vulnerability detection in source code using deep representation learning. So this is a joint paper. So there's this lab, Draper Lab. I actually thought it was a startup named after like Don Draper, but it's actually like a non-profit organization. So and they actually designed rockets. So for whatever reason, they're like designing air-breathing hypersonic rockets. I don't know what that has to do with source code vulnerability. Probably a lot, but I'm not really any wiser. So and Boston University. So basically, I'm going to go over. I have some choice words for the methodology used in the paper. I'm going to restrain myself, as we discussed. But we're going to go over the problem is kind of like, you know, the title is very descriptive. Detecting vulnerabilities from the source code, not the object code, not the runtime behavior of the program, using deep representation learning. So the representation learning part, I presume you should be familiar with. So we're embedding our individual tokens of the source code into an embedding space. And the clicker does, oh, it does work. So yeah, thank you so much. I'll talk a bit of like, you know, a little bit about the background of what is vulnerability detection, what are the classes of vulnerabilities that we often encounter in source code, what are the existing solutions? The existing solutions are not necessarily used for vulnerability detection, they're actually used for program analysis in general, which is a very large field of study with probably like 45 years of publication records. So it's really hard to cover that much ground, but I'll try to do my best. The data sets that they're using for the paper, the kind of pre-processing and data curation that they're using, the methods, experiments and results, some discussion points, some of the things that I found less than ideal. That's probably putting it too lightly with the approach taken in the paper. So the reality of our lives in 2018 is that still the majority of computing cycles are spent running code that is written in C and C++. Now, mind you, C was designed way back when in 1969, so that is like, what, 50 years ago almost. And C++ was probably, what, 1980s? These are not memory-safe languages. Their type systems give extremely weak guarantees. It's almost kind of by definition, type punning is something you have to do. Like you have to like change types and whatnot. And it stands to reason that it's something that you want to have because C and C++, before C, we basically had assembly. If you wanted to write something that's low level or runtime or like an operating system, there was no way of making it portable. So it was great progress. It was a great advancement over what came prior, but in a certain sense, it allows us to do things that are not really, that have not been in vogue in programming language methodology in circles for like 30-something years. So we made a pact with the devil for performance reasons. We are living with the consequences for many, many years now. And no matter how you put it, you have to live with the vulnerable software, and it's not even like necessarily stuff that you would consider low level. So I don't know, GUIs and like font rendering is something that is very high level. I wouldn't consider that like part of the close to hardware stack. But a lot of the vulnerabilities that we are discovering these days are in pieces of software that are doing font rendering on our computers, or like image decoding or zip file decoding, compression, decompression. There's been definitely research in the direction of making languages that are close to metal or potentially can have zero or close to zero cost abstractions, but also be reasonably type safe and memory safe. Well, type safe is not putting it correctly. Like a type system that guarantees certain proper behaviors, but they're still far from replacing the millions of lines of code that we have in C, probably much less in C++. But obviously we're getting there. Google's probably like, you know, a lot of people are actually trying to like re-implement SSL and SSH and OpenSSL and all these libraries in Rust. I mean, I wish them luck, but not going to happen like tomorrow or like anytime soon. So examples of software vulnerabilities that are very much aided and abetted by having languages such as C and C++, array out of bounds access errors. Like, if you're dealing with untrusted user input, so, and this might be anything. It might be rendering a font. You never know. Like these days, you can actually download fonts for like your websites, and like you have custom fonts that you can actually download or generate on demand and send over HTTP. So that is a surface of untrusted user input. And the other stuff, like form validation, stuff like that. If somebody decides to put in 400K of, she does not approve. She does not approve. So, of my talking points. But that you decide to, if somebody decides to put 400K of free-form text input into your form, you better be ready because they can easily, write past your buffer ends and basically go to town in your address space, calling functions and doing stuff that you wouldn't necessarily have expected your code to perform. Undefined behavior. So because C pretty much goes way back, we have a lot of systems that are big endian, little endian, like a lot of different bit orderings, a lot of different ways of doing floating points, a lot of ways of doing binary coded decimal and all those arcane stuff that still C compilers and the C language standard have to support. And therefore, the language, the standard writers of the language took the easy way. They kind of created this almost like no man's land of undefined behavior or implementation-defined behavior. So if you do some stuff in C++ or C, you're giving a blank check to your compiler to do whatever, to like, start a nuclear war, like whatever. Like the compiler is completely free to like change your code as it sees fit. And the most unintuitive part of that, which really affects a lot of cryptography software, like a lot of software that actually tries to do defensive coding. So you check for array bounds, you check for integer overflow and stuff like that. But the compiler actually makes the assumption that your code, if it's sanely written, doesn't really actually invoke any of that undefined behavior. So it just completely optimizes away any checks that you put in place. Literally, your program gets converted to like a null program, like a program, or parts of it, branches of it, get converted to stuff that does nothing. And you're none the wiser. You're like, you're basically, it's a disaster waiting to happen. So a lot of the times, people think they're putting in checks and balances to make their code more adaptable to integer overflows or buffer overflows. And the compiler makes that, reasons backward from that and says, oh, this is not going to happen. Nobody's going to write past the bounds of an array, or nobody's going to put something that is bigger than an integer data type can actually hold into an integer data type, and it's just going to optimize away all your checks, and you never know how far back that can actually go, like how much the effects.
Is that compiler specific? This kind of behavior?
GCC is pretty bad. CLang's kind of better. Like LLVM is a little bit better, not by much. End of the day, compiler writers like the rest of us get evaluated on how they actually compile, how tight and fast they compile the benchmarks. So there's this benchmarking game going on. If you can treat stuff as UB and like optimize away huge parts of the code, yeah, you betcha someone's got to take that route. There's no like work ethic, or like, I mean, it's not work ethic. There's no kind of higher kind of statement of principle that people adhere to. It's just a matter of like not gating necessarily, but if your numbers in the benchmarks are not comparable to the competition, you're not going to get as much business, as much mention. And the most important one, I think, we're reasonably conscientious these days, I hope so, of memory safety problems, buffer overflows, and arithmetic like bounce checks and stuff like that. But violation of higher level contracts. So if you have locking code, you have to lock and you have to unlock. You don't have to. You are not to create conditions that make for deadlocks in your code. So you have to kind of create a topological ordering on your locks, how you acquire them. A lot of people think that it's an easy problem. Like, you have the higher level software, so you have your say HTTP server that's using your TCP stack, that's using your Ethernet stack, and then like the lower level software has to be more careful, or those locks are the ones that are acquired last and released first, and then so on and so forth. It doesn't really work that way. If you're thinking like for networking, for example, which I'm kind of familiar with, if you're thinking ICMP or BGP or routing protocols, there's no clear delineation. Is BGP handling software considered like lower level than like Ethernet frame handling software? Not necessarily. Who knows? Like, and there's a lot of space. So people have this mental model of what sits where in that hierarchy of being lower level and being more careful and like acquiring last and releasing first. And when those mental assumptions don't square with the reality of the code base, you get very subtle bugs. And also, like the other examples that I mentioned, like any sort of decompression, you can potentially have very like unbounded output size to input size ratio. So you can have zip bombs. You have a zip file that actually decompresses to 3 gazillion terabytes. How are you going to know? How do you put a limit that is still not an actual practical limit, but protects you from having to handle all the special cases? Or, you can have many accidentally Turing complete sub-languages or parts of your standards. Basically font rendering. It should be the simplest thing. It's an outline. It's a bunch of Bezier curves. What can go wrong? It has an entire virtual machine, entire stack machine. The only purpose of that stack machine is basically moving around points if your point size is too small. But for all intents and purposes, it's not supposed to be Turing complete, but life finds a way, as the saying goes. So people actually find ways of putting in bombs in these innocuous-looking file formats, and like don't even talk about PDFs, because PDFs can technically are like container formats. So a PDF can contain a zip file that can contain a zip bomb that can actually decode to a legal PDF stream, and then that's kind of like file format exception that you get, and it's really hard. Like a lot of these things don't really occur to us as attack surfaces, but they are, and they are being used for attacks. So existing approaches, and these are existing approaches to program analysis. Program analysis may be done for a variety of reasons. If you're writing a real-time system, you want to put bounds on the runtime and the space complexity of your algorithm. This is not necessarily directed towards detecting vulnerabilities. But vulnerability analysis is a subset of program analysis, and there's 3 broad classes of approaches to program analysis. Static analysis basically means you're analyzing the source code without really running it. So in a certain sense, in a certain very broad sense, type checking could be considered to be a form of static analysis. Your typing declarations are pretty much a very rough contract of how the code works, how the value types mesh with each other. And the type checker, as part of the compiler, basically checks that you're not violating that contract. So type checking is a kind of static analysis, but you can kind of extrapolate from there to checking use after free, or if you're doing a malloc and you're not doing a free for that block of memory, then that's a bug. That's potentially a memory leak. If you're doing a double free on the same pointer, you're probably invoking some random behavior that you did not intend to invoke. But the problem, the theoretical problem, is that we have Rice's theorem, which is basically a generalization of undecidability of halting problem, which basically says that any non-trivial property of programs is undecidable to check. Now, this doesn't mean that you can't try, but it does mean that you wouldn't have any algorithmically sound approach. There's no finitary algorithm that can actually catch or prove or disprove any sort of property or lack of a property for general classes of programs. But still, people try. Now, symbolic execution. What is symbolic execution? Symbolic execution is something like this. This is a very contrived example, but you have a compilation unit. You have a source file, and there's some parts of that source file that trigger certain error conditions or exception conditions, which is outside the ordinary flow of the code. So this is a very contrived example, but you want to kind of trace back from that. Like, under what conditions, how can I translate from the area in my source code when I have to throw an error to the set of inputs that actually trigger that error? I can kind of work my way backwards by treating my variables as symbolic variables or symbolic values and adding logical conditions and arithmetic conditions that actually kind of attest to that effect, attest to that reachability of that part or non-reachability of that part of the code. And that is what symbolic execution is for. Now, people actually use this for all sorts of cool stuff. Like, if you have those crack knees, or you want to crack some software protection, you want to understand what the key would be that actually would unlock a piece of software. You could actually put those constraints, the actual assembly code, into a constraint solver, and you can actually reason backwards from the acceptance criteria into the inputs that will actually trigger those criteria. And by the same token, if you have a program that, for whatever reason, under some conditions has to throw an error, you can work backwards and see what the conditions for that error are. So this is symbolic execution.
Sorry, Alex?
Yeah.
So I'm trying to wrap my head around symbolic execution. So is it, it seems like a rule-based approach to me. It seems like is it input dependent then? So by input I mean the type of code the function, the part of the type of function the code is trying to achieve, right? So you look at the function, you say, oh, it wants to do this, therefore it shouldn't be doing that, or.
If I'm understanding that question correctly, you're asking if it's input dependent. So we actually have symbolic execution engines that kind of almost implement like the C abstract machine, because C, in a certain sense, the C standard is kind of describing an abstract machine. Every statement, in a certain sense, is defined by the effect it has on the state of your abstract machine. The way that abstract machine works, for example, integer x represents some abstract store of memory. We don't think about bits, comprising that part of memory. We don't think about linear address space. We think about named variables. Yeah. And that abstract machine, you can actually not simulate. You can actually specify that in full generality. Right. You can have engines that automatically take fragments of code and understand what that fragment of code does, or do the is it abductive reasoning or adductive reasoning? Do the backward reasoning from that to conditions for the input to reach a certain point in the program, or to not reach a certain point in the program. So it's not input specific in the sense of some human has to actually write a spec for this piece of code, but some human has to actually write a spec for the C abstract machine, for example.
So I'm trying to. So if I'm an expert, if I want to implement symbolic execution,
yeah,
in order to detect vulnerabilities, do I have to be domain expert of a specific area, or are they general?
Not necessarily. Not necessarily. If you have a piece of code and you have a symbolic execution engine, in theory, you can actually do you can actually throw at it the source code of the function, and that's enough for it to actually understand the conditions and actually work out the conditions that are equivalent logically to the paths in your code. But
what will it tell me then? Will it tell me that there is a vulnerability?
It will tell you if some states are reachable or not reachable under what conditions. So I know that this is error. If I'm here, if the program counter is here, I'm in deep trouble. I can work backwards and find the conditions and the inputs that can actually get me to here. So you know what I mean? This is kind of manifest from the source code. I know if I'm here, I'm in trouble. I don't know how I get here from the inputs that I'm given. So what symbolic execution does helps me to actually kind of, not extrapolate necessarily, but work backwards from here and find conditions in these that will get me to that place that I don't want to be, or get me to a place that I want to be. So if you can state your contracts, what needs to be true of the state of your program at every point in execution, you can actually then kind of resolve that into conditions on your inputs that triggers that. The only catch is, and this is a pretty simple function, but then you can kind of imagine if you have an actual realistic code base, these conditions might be extremely hard to, they might actually explode in complexity, and be extremely hard to actually inspect or evaluate by a human. So it's not going to be useful for us. A lot of it is not, and especially when you're talking with finite width data types, you have a lot of accidental complexity coming from the limits of those data types that are not necessarily relevant to some types of analysis that you want to do, but then they might be relevant to other types of analysis. If I'm implementing a multi-precision arithmetic package for cryptography, I care about the limits of precision. So I care about the bounce checking that happens if I'm going over an integer width. Whereas for general logic, I don't care, and it's really hard to separate the two.
Yeah.
It gets pretty complicated to interpret for the human user.
Just to follow up on Hesam's question, just to clarify, who writes the testing function? Is it the symbolic execution engine, or is it some person who writes that function?
No, this function is something that is given to us, yeah. So this is a library that's doing something. It might be GMP, like GNU Multi-Precision Arithmetic Library. And we give this, like we give it to GCC to compile into machine, like to machine-specific code, to object code. We can give it to a symbolic execution engine and just highlight portions of the control flow graph that we want to analyze for reachability or non-reachability, and then it will just spit out the conditions on inputs that will get us there, or just just throw in a towel and say, oh yeah, this is too complicated for me, which is something that is being worked on. Like, we are getting better and better at analyzing larger and larger and more realistic programs, but then there's a limit. There's both a human limit and a computational limit. This is a pretty simple formula or a set of conditions to visualize. If I had like 50 more variables or 50 more conditions to deal with, then it would be of limited usefulness to me in terms of understanding the vulnerabilities or understanding if some point in the input space is really realistic for my program or it's not. And the third approach is dynamic analysis. Now, this is basically running your code and seeing how it behaves. To see how it behaves, to observe the behavior, you actually have to instrument the code. So you have to be watching over the program as it's running and see if the behaviors are what you consider to be within the bounds of normal behavior or not. One problem for this is, generally programs have very complicated control flow graphs. They have a lot of special cases. The special cases interact, and you have exponential explosion of the state space. So programs are very compact representations of very complicated state charts in a certain sense. And once you're doing this, you're dealing with that state chart directly. So it's really hard to make sure that you're covering the entire state space. And it's very resource intensive, both because instrumenting programs is expensive. Running something and observing it is going to be less efficient than running it and not observing it. And sometimes you actually have Eisenbugs. You have actually behavior that is only triggered because you're observing what is being observed and not otherwise, which is another thing to be careful or to be cognizant of. And but then again, they are used to great effect, and all of us have probably heard of it. Fuss testing is one example. You just generate random inputs and try to crash programs that are working with user-supplied inputs. Now, naive version of it is basically you generate random stuff, you mutate random stuff, and see where that gets you. More kind of profile-guided fuzzing, which is kind of exemplified by AFL, is that you're instrumenting your branches in your program. You're looking at the control flow graph of your program. You're looking at the flow chart of your program, and you're seeing how much coverage you're getting. You're mutating your inputs in the direction of getting maximal coverage. You want to get maximal exposure of all the paths that the program can take through the control flow graph. And you gauge the fitness, if you will. It's kind of like a genetic algorithm. The fitness of your inputs or your mutation methods by how far they get you at exploring the unexplored corners of your state space. And by this, you can actually see how it kind of relates to symbolic execution as well. You can actually use logic solvers and symbolic execution engines to kind of guide the fuss testing aspect. So if you're hitting a hard to cover branch or a hard to cover condition, you can actually kind of sometimes you can actually invoke a reverse symbolic approach and understand or work backwards from what conditions might actually trigger execution of that part. But this is actually used to great effect for a lot of safety critical software, but it's very resource intensive. So it's not really scalable to the scale that we want to make it to be. Now these were the three approaches. Now the data set and how they got to the data set. This is the most, or one of the weak points of the paper. They use common weakness enumeration, which is a list of common software weaknesses. Uses unified terminology to provide a common ground for discussions regarding software security, and allows software vendors to quantify the security characteristics of their software in a uniform manner. Quite debatable, but still. I can see some descriptions, some of the classes of vulnerabilities or weaknesses that are actually in that standard. Buffer overflows, and I don't know what this is exactly. I don't understand this. Improper restriction of operations within the bounds of a memory buffer. But like these kind of seem like the same thing to me.
The first one seems to be you just give the buffer something that it wouldn't handle. So
not necessarily. You're not checking your input. You're not putting a limit on input length.
Right.
What is the improper restriction of operations?
So you can have recursive operations that can generate. So the input isn't necessarily large, but the result of the operation on the input can be larger than the buffer.
So depth overflow.
No, but like decompression. This is I don't know. This is very unclear. But I mean, I didn't go deeper into it. 469 is pointer arithmetic. Pretty much like doing arithmetic operations on pointers to do stuff, which is very dear to C++ programmers, and you actually need to do it sometimes. Null pointer dereference, buffer access with incorrect length value. This is also a concurrent execution using shared resources with improper synchronization, improper input validation. So there's definitely there's definitely value in the common terminology, but some of these things are kind of fuzzy themselves. So it's really hard to determine what kind of category or what kind of ID we have to assign to a certain type of vulnerability. With that said, they use a standardized data set that comes with labels for these categories, and they kind of divide these into things that could be security sensitive or can actually lead to security issues with the software, and things that are purely basically fail crash vulnerabilities. They don't have any security attack surface. And they use the standard data set, which is synthetic, is SATE IV or SATE IV. It's not, and they also use the open source like Debian Linux and GitHub repositories. In all cases, they actually deduplicate their functions through some mystery deduplication method that they don't really disclose. It's just like, oh yeah, we lex the functions. If they're substantially similar, we remove the second version. If it's after that, they do some basic block analysis or control flow analysis of the functions. If they actually have substantial overlap, they actually remove those duplicate versions as well. And the most problematic part is for open source code, they actually label those using 3 existing static analysis tools. So the ground truth labels are, I'm pretty sure, like very noisy. I don't trust that this method can actually give us very reliable labels for the bulk of the code that they're using. And roughly 10% of the functions, and they actually do this at the function level, which is, I guess, a pretty fair way of doing it. They want to have enough training samples to make sure, the deep learning-based approach is actually viable. So per program, per compilation unit, probably wouldn't work. There would be too few training samples for the algorithms to pick anything up. But where it actually kind of falls short, in my opinion, is that the real data sets are both much larger than the synthetic and hand-curated data set, and they're much more unbalanced. So roughly 95% of the functions that they examine are not vulnerable. I don't believe any of that. I'm pretty sure closer to 20% of the functions are actually vulnerable. And another point to be made, this is very C and C++ specific. Now in C and C++, general types of vulnerabilities that we were talking about, like use after free and stuff like that, or like improper locking protocols, or improper implementation of locking protocols, you can probably capture those at the level of the main functions or the main business logic function of a program. Whereas for other languages like object-oriented languages, for Java or like C#, which are more kind of development by accretion and automated tools, your business logic is scattered all over the place. So you actually have to like do trace-based analysis. So you actually have to look at a path through the execution of the program to see if all the proper invariants are respected or not. So this probably works, and I mean, to be fair, most software that suffers from vulnerabilities, memory safety and buffer overflow and other types of vulnerabilities that we are discussing here is probably written in C and C++. So this is a very fair approach for those.
So state V is manually labeled, and Debian and GitHub are labeled by static methods built on top of state V. But like
no.
state 4, sorry.
No, not necessarily. So they don't make it clear, but I think the error messages or the warning messages from the static analysis tools are bucketed into one of these categories. So kind of, sort of, they kind of translate from the error messages of the static analysis tools to these categories, and then kind of wholesale binarize these categories. Some of them are security critical, some of them are not security critical, and then kind of that's how they binarize their labels. So that's the reason I'm saying that this is a very noisy way of labeling their data sets. But to be fair to them, if they wanted to get the volume of data that they need for their algorithms, probably that's the only way to have done it. So
what you just said, does that apply to state 4 also?
No, state 4. For state 4, we have these codes. So we have ground truth that we presume is reasonably precise. But yeah, and the only part remaining is basically how you actually evaluate or how you actually assign these codes to security critical or non-security critical. Right. So that's the part that they actually choose. But for these, we actually use the error messages from static analysis, and they don't make it clear at all. So we actually read the paper many times to actually kind of.
So by these, sorry, just to make sure, you mean Debian and GitHub? When you say
yeah.
These. Okay.
Exactly. So they actually run 3 static analysis tools. Yeah, if you want to make a comment.
So SATE IV is a dataset that is created by, it's an artificial dataset created by some US government agency who had an interest in creating these static analysis tools. Yeah. So it is completely labeled with the exact vulnerabilities that there are. So it's sort of a toy dataset for static analyzing tools to like compete against each other. The remaining 2 are real world datasets. The first one's just
in a certain sense, so like we have model checking, like bounded model checking tools like PDS and others, the people in high assurance software. So if you're writing software that controls, I don't know, ICBMs or like, I don't know, like weapon systems, you want to use like PDS or other like bounded model checking software to actually test for undesirable conditions or undesirable states in the control flow of your program. And SATE is kind of designed to simulate, or not to simulate that. It's designed as a benchmark for those things. Now, general statistical analysis tools are not really meant for that. They're kind of more for the more pedestrian kind of developer population. But you can reasonably map from the errors and warnings that they put out to the categories of SATE IV. So that's what they did. But they don't go into detail. The only thing they do, they actually put their data set online. So it's, I guess, yeah, the interested reader can probably check, but if that's really a reasonable thing to do for the volume or the number of functions that they have. So basically, after curation and deduplication, their pass rate is closer to 10%. And apart from this synthetic data set, their data sets are very imbalanced in favor of non-vulnerable functions. And the 5% is very, I don't know, I don't really believe that number, but then to be fair to the authors, it's not like, you know, I'm not going to go and like label stuff by hand and say, oh yeah, this is a vulnerable function. So yeah. So pre-processing, they do a lexical analysis or tokenization of the source code, and they just kind of remove stuff that is not relevant. So comments, I mean, it's arguable if comments are relevant or not. I presume the existence of comments is a signal that the code is probably higher quality, but then who am I to judge? Oh,
My apologies.
okay, yeah. C and C++ keywords are retained as they are. String and character and floating point literals are replaced by generic placeholders, which stands to kind of you know, scrutiny, because people don't generally use, I mean, if you're not writing TCL, you're not generally using strings as indexing variables in your arrays or something, or like, so only integers have a relevance as far as their value, their actual value is concerned. So every other thing is kind of replaced with a placeholder that says, oh, this is a string literal, this is a floating point literal. Integer types are tokenized as an actual value that they contain, because a lot of stuff is off by one errors and things where that actually is kind of relevant and has some significance to whether or not your code is vulnerable. Data types are homogenized. So basically anything that is an unsigned integer of 32 bits is, and D words are in here as well, which I have some problem with, because again, I think there's some significance. If you're using D word, you're basically adhering to standards that were around in 1992. Anything written past the year 2000, I presume, is using one of these variants. So U32, UN32 underscore T or stuff like that. So, but then again, like, you know, to be fair to them, this is a very sane choice. So you just kind of normalize on your data types, because, well, you know, there are a lot of type defs in C compilers, and you can't really cover the entire set of things that you see in the wild.
But even there, like, I feel like you mostly see those in like places where you're talking directly to hardware registers, or maybe in really low-level image analysis where you're maybe doing some byte-level optimizations. Like, for most workaday code, using those is not really considered best practice, because now you actually steer the compiler away from tailoring it to your hardware.
Exactly.
So
exactly.
It's only, you know, yeah.
It's exactly at the interface to something that is that is not your native like word length, or doesn't speak your native word length, that you actually have to explicitly specify stuff.
It does make me wonder, like, what would it be like if you could tell the compiler this is the anticipated upper bound for this value, and allow it to pick the most performant type present on the underlying hardware. Like that could, I mean, I'm surprised that I've never seen that before. Because if you know you're never going to overflow an N16, most of the time you're probably going to want to go with whatever your CPU's native integer type is anyway. But there are use cases where you could sock a whole bunch into a big word.
Yeah. That's the thing with C specifically, because C is not one language. It's probably a very it's probably 30 languages pretending to be one. So it's if you're writing C to interface with like a COM+ interface, or like talking to some piece of hardware sitting somewhere, you probably your dialect of C is going to be very different from the general I don't know, CS 101, or like whatever the course is going to be, C language that people are taught these days, or probably not these days. The problem with this type of lexing is that generally C and C++ don't really lend themselves to that separation of phases of lexing and parsing and ASD to CSD and like intermediate language or intermediate representation and then object code. And one of the problems that people are probably like aware of is the most vexing parse. So the most vexing parse is basically based on lexical information. You can't tell apart a function call in C++ specifically, but also, I mean, C99 probably suffers from the same. You can't tell apart a function call from an object or a class constructor call. So if you look at it, most people actually don't realize this, but if you look at it, it's basically the same. It's only the force of convention and naming that lets us disambiguate the which one is which. There's some loss of information from considering all these things as being the same. So the example I can come up with, if you're using some actual, honest-to-God hash table that is indexed by strings, you probably are using strings in a way that for most or more ordinary C code, integers are used for. You might actually use them as indexing placeholders as well. But then again, like that is not necessarily captured with like floating points. If you're doing any sort of bit level representation or casting of types, then it is utterly irrelevant. So there's like there's this piece of code that is from, I think, from Doom 2. It actually does treat a floating point number as an integer, which turns out to be almost equivalent to getting a log base 2. And then like, you know, it's the inverse square root. You can actually search it. So it's, you know, people actually do that stuff for very legitimate reasons. Sometimes it works. I mean, it's debatable to what extent such a static analysis tool should or could be reasonably assumed to be able to like capture those nuances. But then again, like, you know, there's legitimate use cases for treating types as placeholders for vectors of bits. So,
Alex, can I ask a question? It says their vocabulary is 156 tokens.
Yeah.
Does that mean so even with integers that are represented as the value of that integer, they still were able to get to 156?
This is something, yeah, your guess is as good as mine, but I mean...
I can clarify that. So integers were characterized one digit at a time, so there are only 10 tokens for it. Right.
Could you repeat that for the camera, please?
Oh yeah, sure. Did I move out of bounds?
Oh, no.
Yeah.
Your answer.
Or
could you
sorry. I didn't get that. So
So the reason there's 156 is because there were like each digit in an integer was like lexed individually. So you only had 10 tokens for integers and like you had if any integer got tokenized as a stream of one-digit tokens.
So yeah, to rephrase that, basically you're treating your integer literals as being a sequence of digit tokens, which helps put a limit on the number of tokens that you have to consider. But also you kind of rely on the next layers that we are going to discuss to capture the sequence structure. So if a certain sequence of digits appears in two different places or appears off by one in two different places, you can kind of capture that as well. Was that a fair rephrasing? Okay, yeah. So the intuition for their deduplication is basically either if you're lexing to the same token stream, with this specific tokenizer implementation, you're the same. They have a very unclear. It's in a footnote. They have a very unclear way of deduplicating further. So if the CFG, the control flow graph of two functions, turns out to be the same, and their basic blocks are basically containing the same set of instructions, they kind of surmise that is basically the same function but copied over, which does make a lot of sense because they're very fundamental, like TCP sockets or like libm, like math functions. They are like duplicated all over the place. If you actually look into a lot of proprietary code bases, even you actually find a lot of BSD licensed code from like libm or TCP sockets and stuff like that. So it does make sense to prevent leakage that way and remove stuff that are exact or almost exact copies. So the method, the structure, I have to actually go one slide further. So how they do it, this is basically encoded. The tokens are basically encoded by one of the 156 token representations, but they're then embedded into a k-dimensional. So this is the direction of dimensionality of the embedding by a k-dimensional embedding representation, and the k is was found to be equal to 13. They have two versions of their actual feature or classifiers. One was a convolutional feature extractor. The convolutions are have a receptive field size of m. So each convolution is looking at a window of size m in the token sequence space, and they have n total filters. So each one of these n filters, one might be looking for the pattern of malloc and free. One might be looking for the pattern of socket bind, I don't know, listen, accept, whatever, like, you know, whatever TCP socket calls or whatever other type of resource usage patterns that are very pertinent to the types of vulnerabilities that we want to find. They do a max pooling along the sequence dimension, kind of the symbol sequence or the time dimension. So they actually, each of these, so this is the axis of n, the number of convolutional filters. This is the axis of L, the length of the program. And this is the receptive field of our filter. We actually do a max pooling along this direction. So out of the entire sequence, we only keep the most prominent activation for each of our 512 features. And we're only looking at a local context of nine tokens to make that decision. Once they've done this for the convolutional structure, they actually put two dense layers. There's a 50% dropout between this max pooling layer. And all this was not clear at all from the paper. We had to read and reread the paper to actually figure it out. But I think this is the closest interpretation to reality. There's no code coming with this paper, so take that with a grain of salt. So there's a 50% dropout in this layer, and this is a 60. So this is technically a 512 dimensional layer. This is a densely connected 64-dimensional layer. Then you have a 16-dimensional layer, and then you have a 2-dimensional layer. For whatever reason, they didn't use a sigmoid activation function, despite the fact that their labels are actually binary. But there's kind of sort of a reason for that we will get into later. And they actually trained using cross entropy on these labels. So they actually backpropagated to learn the embeddings here. They did experiment with other ways of unsupervised initialization of the embeddings, but that didn't really work out. Or it didn't really improve over just learning with the labeled data set. And they added a perturbation, like a noise term, to their actual embedding values when they are propagating to the output that they kind of claim is regularizing or is helping performance. And to top it off, they actually, after backpropagating the error and establishing these embeddings, they actually used the random forest classifier on the max pool features. And they claim, I mean, they don't claim, their plots definitely show that it's performing marginally better. And there's another recurrent version of the same structure. So you get your k-dimensional, in this case 13-dimensional embeddings. With a receptive, I mean, there's no receptive field here. You just kind of feed your embeddings into a two-layer 512-dimensional GRU architecture. And this is the part that we had the most trouble with. It kind of makes sense if you're thinking of like high-dimensional geometry, but they actually do another max pooling in the time dimension, but they're like individually basically max pooling along the 512 dimensions. I can kind of sort of, justify that for myself.
Just to clarify, so is this the same architecture as the previous?
It is, no, it's up to this point, it's the same,
so is it,
except that these are like,
yeah. Now you have a recurrent network.
We have a recurrent, like instead of two dense layers, 64 and 16, before the final classification layer, we actually have a recurrent network, which is two layers of 512.
The previous one was more CNN-like, and
this is RNN, yeah. That was CNN, this is RNN. The CNN marginally outperforms the RNN, so they actually kind of report most of the results with the CNN. But then again, they do another component-wise max pooling, which doesn't really make sense at all. doesn't really make sense at all from like first principles, but when you think of it, if the embedding layers are doing their job, and these are huge embeddings for the space of 156 tokens. These are like 512 dimensional. They're probably very disjoint in terms of semantic connotations.
So it's pooled across the individual dimensions?
Yes, across time. So for each of the 512 dimensions, they look at all the tokens and see what is the most prominent activation along that dimension. So it's like, it's basically, yeah, it's like,
still weird, but
it's,
I mean,
it's very weird. It's really hard. Like, we actually have to like go back and forth and read through the paper many times to actually make sure that we are not. So this is not our like take on how they did it. So
I guess I'm trying to understand the intuition behind it. Is it the intuition would be that I don't know, int, for example, as a keyword would have something more like more of an activation as opposed to new as a program keyword?
No, that's the thing. Like I think if you're basically the bet they are making is that 512 dimensions is enough to capture all the ways that a program can show errant behavior. Maybe like one of them is like use after free. The other one could be like double free. The other one could be not doing the proper like song and dance for like locking and unlocking stuff. And all these dimensions are kind of separated in that high dimensional space. If you're like but if you're back propagating on our embeddings, it does make sense that they kind of separate out and they kind of specialize in different aspects of the source code. And if we are only interested in indicators of presence of certain patterns to make that judgment of whether or not a function is vulnerable, we only want to see if something, some defect is present or not. So if each dimension is basically representing some sort of fuzzy notion of a defect in the source space, it suffices to actually only, or not only, like take component bias maximums over. So want to see if defect 1, dimension 1, use after free is present, or if dimension 2, which is some other as yet unknown like type of defect in source code is present, so on and so forth.
Right.
Yeah.
So you're, I think I kind of, so what I think would make sense is that in their architecture is that you're looking at RNN and there are actually states. So is how much I wanna, how much of the entire sequence I wanna look at, kind of like attention. But you're saying, but it's more limited than attention here. So you're saying that I have a sequence of I don't know, a sequence of codes, and then because I think it's a function that is input to the network, right? You say so if that is the function int ID whatever equals int whatever. Then you want to say, only int, for example, is enough for me, or I need to have seen the entire, I need to observe the entire sequence as a encoding, as a state, if that makes sense.
Pretty much, that's like that's what the GRU dynamics takes care of. But also because all these things, this piece of code is just one piece of code. There's one surface representation, but from this surface representation, we might kind of surmise that we can get a bunch of indicators. Like, does it have the use after free defect? Does it have the improper usage of the socket library interface defect? Does it have? I mean, these are like human friendly labels or whatever. We never know what it's learning. But I presume if you're going all the way to like 512 dimensions, that's probably more than enough to cover the entire space. So the dimensions are necessarily decoupled as far as their semantic content is concerned, but they're coupled by the fact that they're coming from the same surface representation. This is the same piece of code. If it has defect A and defect B, that's coming from the same thing. So the interaction of different state components is kind of justified that way, but it's really kind of a hard pill to swallow. I understand, like this is on my paper, so that was the best I could come up with in terms of an intuition pump for myself to kind of understand how it works.
To understand it, I think the only way I could understand it was compare it with attention, because a limited way.
Attention in what sense?
Because in attention, you look at a sequence. Exactly. Okay. So you have a sequence of embeddings in attention, right? Okay. And well, in NLP at least. Then when you want to generate something, you want to see which embeddings I'm in order to build my representation, to make a call, make a decision, which embeddings or which state am I looking at? What matters basically and what doesn't matter in a sequence, right? What items in a sequence do matter, what items don't matter.
I have to think of it. The way I looked at it is that like the maximum operation is more of a disjunctive kind of logical thing. Like this code could be defective if at any place in the source stream it contains A or B or C or
Correct.
D or like, you know,
Yes,
so
the
on
only
and so
difference
forth.
is that you're looking at state, so you are encoding the past.
You are encoding the past in the sense that yes, you're encoding like maybe like one. I mean, like I'm not pretending this is how it works. I don't know, but I mean like nobody knows. But I mean the first state would be like, you know, the first state dimension or the first state space would be, to your point, would be more of a time evolution factor. The second one would be more of a disjointed representation of the defect space. You know, the first dimension is, do I have this class of defects? The second dimension is, do I have this class of defects? And ultimately, that I have this class of defects or not in the entire source code is determined by the disjunction of that, having that defect at different places in the source code. So the max pooling along the time dimension, along the sequence dimension does make some sense.
So when you say dimension, you're talking about the time dimension, not embedding dimensions, right?
No, it's max along the time dimensions.
I know, but you said the first dimension talks about something.
The first space, I didn't say dimension. The first state space is more of a capturing history or capturing arbitrary displacement or like, you know, selective forgetfulness, if you will. The second dimension is more of a, you know, when we actually kind of separate what we are considering different categories of defects. But this is like only like putting a human interpretation on it. Like I don't really know. Like this is more of a meta kind of architectural concern. You never know what it's doing. So, and you're gonna have and this is gonna make your feature representations. You're gonna have the same kind of dense structure, and then like, you know, the same kind of two-pronged solution that you actually backpropagate using your end-to-end neural architecture, but then you use your intermediate level features as inputs to a random forest-based classifier. Oh, it's actually 256, so my bad. It's not 512.
It was 512 the previous architecture.
Oh, was it? Okay, so my bad.
It was 512 kernels.
So this is basically saying the same thing. So this slide could be considered redundant at this point, but so they use functions of between 10 and 500 tokens. Off the top of my head, considering that they're considering or treating digits as being separate tokens, I don't know. Like 500 tokens seems a little bit small, but then again, I mean, I might be totally wrong. But they actually only consider a certain range of length for the functions, and they actually pad everything to the standard 500 tokens. They train in batches of 128. They use Atom for optimization. For the convolutional, this is probably 10 to the minus 4, or is it?
Yes.
Yeah. So the loss is obviously from the neural part is cross entropy. What is weightage?
So since there is class imbalance, they kind of weighted the negative class, like errors on the negative class much higher than the errors on the positive class.
So last term is kind of proportionately weighed towards giving more importance to the vulnerable samples as opposed to the baseline non-vulnerable. So
oh, maybe that's why they're using cross entropy. Because if it's just a logistic function, I'm not sure how you would weight the loss.
So that they are using cross entropy is also because they actually kind of like, you know, the paper is really badly written. So they don't really just so it's kind of like, you know, they put the cart before the horse. Like they actually, after all this is said and done, they say, oh yeah, we could actually train on the individual CWE labels as well. So it's really, I don't really know. I was not in there, like I was not, this paper has like 10 authors, so I don't know how it actually kind of transpired between them, but I guess they started like with,
two terms, right? On the left and right, and you're summing them.
Yeah.
So you can technically weight.
No, but that's the thing. The loss is per sample. So the loss is the cumulative, like your empirical. Is that your empirical loss? So if you're weighting your negative samples, you're both weighing the p log p and the 1 minus p log 1 minus p similarly. It's just that for a certain class of samples, you're weighing those more. You know what I mean? It's not like you're treating one part of the equation differently from the other part of the cross entropy. That's kind of my presumption, but I have to actually write it down to verify.
Think about it more in the discussion.
But I think that is the case. So it's not like they're treating the p log p term differently from what.
Yeah,
Yeah. So it's
so my understanding, just a comment I'm gonna slip in, is that it's usually on the class, right? Because it's either this class.
Oh yeah,
it's
for the
either
positive.
P
Oh
or
yes,
minus,
yes,
right?
yes.
1 minus P, right? So that's because they're talking about positive class and negative class. So
It's assuming if there's 2 classes. If
Yes.
there's 10, then it would be across all 10.
right. So those 1 and
do you fold it into like how do you the empirical risk function? How does it actually decompose into like 2 sets of classes? Do you
Just multiply this p log p by something, or 1 minus p
log 1 minus p? Yeah.
Because technically
One
they're
of
weighted
the
by
first-
half, right?
So if the probability of such a class is closer to 0, then and that's what you want, then there is no cost to it, right? So that's cost. That's one part of the term. The other part of the term is that the probability of class being close to 1.
No, aren't you taking the entropy? Aren't you basically taking the and I have to think about it, taking the empirical divergence of your reported probabilities versus the true labels when you're calculating like a per sample like loss term. So I'm thinking, that per sample loss term has both the p log p and the 1 minus p log 1 minus, I don't know, like I might be totally wrong, and it's like
this sounds competitive at this point, so let's
okay, yeah, but I don't know, like I didn't really I had enough trouble actually understanding how they actually did their stuff. Like a lot of the crucial details are left out of the paper, so I didn't really even write down the I took them on their word for that part, that they are like using the weighing thing. So so on the split is 80 10 10 for training validation test. Their experiments and results. So they use the baseline bag of words, so there's no sequence information preserved, and they work on the level of characters. A lexed bag of words with a random forest classifier. RNNs end-to-end, CNNs end-to-end, RNN features with random forest classifier, CNN features with random forest classifier. They actually do the area under the ROC curve, but also the area under the PR curve that I haven't seen anywhere else, so it's kind of, I don't know. So I have zero idea what should be a reasonable range for this. It should be more than 1/2. But actually, some of the reported results are actually less than that. They're like 0.43. So, but what do I know? So I don't really know if that's reasonable or not. And because their data sets are so imbalanced, they actually use the Matthews correlation coefficient, which is one of those like folk wisdom things that is a better metric if you actually have heavily imbalanced data. I've never seen it like put into like theoretical, like sound theoretical footing, but it's part of the lore of I guess machine learning. So they use this as well, and the F1 score. But
Alex, what's the lexed bag of words?
So they do a bag of words representation, but they don't look at individual like keywords. They just look at lexical classes, I guess.
Oh, okay.
So but if you want to add to that.
So the baseline bag of words is basically bag of words separated at like standard
Spaces.
word boundaries like spaces, commas, bracket opens or whatever. Next bag of words, they pass the program through their custom
Tokenizer,
mixer. Run bag of words fitting on top of the output of that, and the rest is
the next bag of words is less sparse.
Probably less sparse, but also less kind of
yeah, so the next bag of words would have a dimensionality of 156.
Yeah. So and the F1 score. This is their precision recall curve. So I don't know what to make of it, like the 0.352 or the 368, and like all these. I don't know if they are supposed to be good or. But the overall trend is kind of consistent. They're convolutional plus random, so convolutional feature detection plus random forest classification seems to be beating everything else. And this is basically the precision recall curve for different approaches, basically. So you can see the CNN plus RF is,
Yeah.
I mean, for some definitions of closer to this top right corner, but
so the precision recall doesn't seem to.
Yeah, it doesn't seem.
If they're using F score and if it's F1 score, so it's the harmonic mean, I think that they're equivalent. Like they should be the same.
Well, no, but I think you get a finer grain detail here, right? Because
it's just unweighted way of looking at it. Because with raw precision, raw recall, as opposed to I don't know the F score.
Yeah, I mean, I've seen something similar. There was somebody who was pitching something like this for generative analysis, and the main thing is that if you're on the recall, it allows you to look and see if you're doing mode dropping or spurious mode creation, basically.
Oh, okay.
But that's the thing.
But it's technically encoded in the
F score.
Yes.
It's just a different way of weighting it. So you're looking at raw scores.
Yeah.
But this is basically their results on this kind of contrived PR AUC. Though it's an actual honest to God PR curve. So that's actually legit. This is their TPR FBR, and you can get see. It's like I don't know. I'm not going to judge which one's better, but because it's not clear if the CNN plus random forest is actually better than pure CNN. So I guess they just wanted to I don't know. They wanted the CNN plus random forest to be the winner, and they kind of picked their metrics to support that, I guess. But I mean, yeah.
Some accusation.
I don't know. It's like a lot of the things don't really make sense in the sequence that they are presented in the paper. It seems like some of the experiments were done before, or the way they're reported is not really the way they were they actually came up with the results. But then again, and they're they kind of make the claim that they can use feature activation importance or visualization of feature activation importance to actually signal to the users, to the human users, where in the code the vulnerabilities lie. This is kind of one of those, it's kind of a type hunting thing, because you're actually assigning your union using the first union type to this buffer that contains Unicode characters, and then you're actually treating it here inside this local scope as the second type. But I would be really, if it was up to me, I would say that this is the place where you have to be watching for, because this is where you're breaking the already weak type contract that you have with the compiler in a C-like language. But then again, it's actually putting much more emphasis on when you're actually writing to the same. It's kind of almost doing like a pointer analysis, like an alias analysis, as opposed to finding the root cause that is you're co-opting a union into two constituent types, or treating one piece of memory as two types of data. So I actually have I have my questions. I don't think this I mean, in terms of alerting somebody that is looking at the code to what could be a potential area of concern, this is as good as any tool. But if it were up to me, I would say that this is the most problematic statement here. So I don't really know. So discussion points. There are
That's next section. We'll take a break.